Okay, welcome everyone. Today we're happy to have Asif Equbal from chemistry, who is going to tell us about molecular spin qubits for future quantum technology.
All right.
Please.
Thank you very much, Hisham. Thank you everyone for being here. And as you heard, like I'm from chemistry, so this is something which is new for me, but something I'm really interested in for future research. I have been working in NMR, basically spin resonance, for last 8-9 years. And at this point of time, I want to utilize all my knowledge into developing molecular spin qubit for future quantum technology. I advance my slide. So it really amazes me, like when we think all the information that's there in this world, all those information, they can be translated into binaries. So this is something as a chemist, like it really amazes me, like any photo, any audio file, any video, everything, computer interprets that as a combination of zeros and ones. So those who are into quantum computation, they are not surprised by that. But those who are new to quantum computation, for those people, I would like to give one example how we map all the information in binaries. Suppose you have a picture here and we want to convert this picture into binaries. This picture can be divided into pixels, and the brightness of each of those pixels, they can be represented by a string of bits. And we can have a code, which is like if all the bits are 0, that pixel would represent a black pixel. And if all of them are white, then it would be a white pixel. So with these combinations of bits, we can create this entire picture. So it is as simple as that. And you now may think like, okay, so that was a simple example, but how do we do a more sophisticated application using computer? Like how do we do some MATLAB calculation? How do we watch Netflix or do online transaction or do Zoom, for example? So for all of it, there is a computational stack that we follow. It's every time we do something, those stacks are followed, and we can go from bits to application. And one of the important stacks is gates. So we do something to these bits and we do some manipulation on the bits. And manipulation is basically converting the bits, which is like combination of 0 and 1. And there is a specific kind of gate for any desired operation that we want. So any gate will take the input bits and it is programmed to spit some output bits. And in a real computer, there are many gates, and those gates, they combine to form circuits. But just to give an example of how why gate is important in order to do any processing. Suppose we have this black and white picture, and I want to invert the color of the black and white picture. What I can do is I can do an inversion gate. I can apply an inversion gate, and all the bits which were like, say the white was 0, 0, 0, it will be converted to 1, 1, 1. So we can go from black to white. So this is again a simple example, but it's basically this logic which is applied in any computation that we do. So we have many gates and multiple gates. Sometimes they form a circuit, and many circuits, they can form an algorithm. And when we do any application, it's basically a set of algorithms that we use in any application. So what we do is basically we are using classical bits, which is in computer, we are basically passing signal through transistors, and either the electrical signal is blocked or it's allowed. So the bits that we have in computer is 1 or 0. What we are doing with electrical signal, we can do that thing with any other thing in the nature. For example, we can have a molecule, and that molecule, for instance, it can have two different conformation. The molecule can be in the form of a chair, or it can be in the form of a boat. It can have two different conformation. And if we have a control to translate this molecule from one form to another, then we can do calculation even with this kind of molecule. And that's the idea of quantum computing. So we have molecules, we have many systems that follow quantum nature. One interesting and most important thing about those molecules, which is different from classical bits, is that unlike classical bits, which are always either 1 or 0, either the current is passing or it's blocked, in molecular system, in quantum mechanical system, we can have superposition, meaning the molecule can be both in chair form and boat form simultaneously. So it is both chair and boat at the same time. And this is something which is counterintuitive, but then we know that superposition do exist. So the idea of quantum computation is to use this property of the quantum nature and do computation. And if we develop quantum computer, not necessarily we would be able to do all the computation faster. There would be specific computation which would have quantum advantage. And one of such computation would be some search algorithm. For example, if we want a solution for this maze, classically, one has to explore all the possible routes one by one, and then the total time to solve the problem would be basically sum of all the times. Quantum mechanically, we can do a search algorithm which takes different routes simultaneously. And this is using the principle of superposition. The idea here is simple, similar to classical system. We need to have bits, and then we apply some gates. The only important thing here is that, or different thing here is that, when we apply classical bit from 0, 1, we go to something which is 0 or 1. We never combine two of them. In quantum world, we can have gates where, say, we go from 0 to combination of 0 and 1. So for example, this bit, it is a superposition of 0 and 1. So this is what we want to do. And the idea of quantum computation, it's quite old now. The idea was first postulated by Feynman in 1981. And after that, many algorithms have been developed which can solve the quantum computation. For example, Shor's algorithm. And this is something which was later on demonstrated experimentally. In 1998, a first 2-qubit based quantum computer was developed using NMR spectrometer. And very recently, Google developed a quantum system where they can show that, in fact, quantum computation can have advantage over classical computation. But still, we are not at a stage where we are able to solve some real world problem with quantum computer. It's developing stage. We are in a stage where how classical computer used to be like some 50 years ago. It used to be like a big instrument. And even now, for quantum system, we have something similar where it does not look like a computer, but rather some heavy instrument. But the same idea is implemented in these systems. The challenge in building quantum computer, the real challenge is developing a qubit system. So the quest for ideal qubit is still on, and that has got recently very intensified for the reason that a lot of different players, big companies, many governments, they have started heavily investigating the quantum system, the qubit system. There are, at this point of time, there is no clear indication what would be the best qubit. But there are different systems which are being explored. And for example, IonQ, which is a quantum computing venture, it's using trapped ion to basically as a qubit system. Google and IBM, they are using superconducting alloys as a qubit system. Intel is using spin-based qubit to develop its quantum system. Many academic labs, they're using laser, like quantum qubits does not have to be a particle or a molecule. It can also be wave, it can also be light. So many academic labs, they use laser pulses as their qubit, and the polarization of light serves as the as the bits there. Microsoft is working on topological qubits. And at this point of time, it's not very clear which would be the best qubit. Each of them, they may be suitable for solving a certain kind of problems. Today, I want to talk about De Vincenzo's criteria, the criteria that he postulated, which would be universal to all the quantum computer. He postulated 5 principles that must 5 requirements that must. With this quantum circuit, let's understand what those 5 criterias are. The number one thing is the qubits have to be scalable. In present day computer, we have systems where we are using millions of qubits. Maybe like 500 million qubits are being used for computation. Bits, not qubits. 500 bits are being used for computation. So can we develop qubits which are also scalable, if not to that proportion, but at least say 100, 1,000, 500. So at this point of time, we have not achieved scalable qubits. There are qubits, but then it's very much limited in what it can perform. So scalability is one issue. The other issue is initialization. So if you, for instance, see this quantum circuit, there are 3 qubits, and in order to perform any calculation, we need to be sure what is our starting condition, in what state the qubit is. Is it 0? Is it 1? Is it combination of them? So we need to be able to initialize our qubits very well. So that's the second criteria. The third criteria is the qubit. On the qubits that we choose, we should be able to apply universal quantum gates. So in this circuit, you see there is Hadamard gate, H gate, X gate, and then we have C0 gate. So in order to perform calculation, we should be able to apply all the gates. The fourth criteria is since we are applying these gates in a sequence, the quantum information that each gate is producing, it should be preserved till the time we are measuring those information. So having long decoherence times on qubits is also very important criteria. And the fifth one is we should be able to measure qubit individually, each of them, so that we know what information got encoded in those qubits. So these are the 5 criteria that need to be satisfied. And I'm sure most of you know about these things. So I now want to venture into the spin-based qubit. That's the first quantum computer that De Vincenzo developed using NMR. And so this is something which might be a bit technical for those who are into theory of maths, but spin is something which is very well utilized in spectroscopy, for chemistry, for biology. And we can think of spin to be like a ball of magnet that is rotating, but in reality, spins are not ball and they are not rotating. So, but they produce effects which are similar to that. So it's like a spinning magnet which is precessing in a magnetic field. And when we put these spins in magnetic field, the energy levels become non-degenerate. So for a spin half system, we can have 2 energy levels. In one energy level, the spins would be precessing along the field, and in the other energy level, the spins would be precessing opposite to the field. So we have 2 states, and these 2 states, they can serve as spin qubit. And the good thing about using spins for qubit is that the spin physics of spins, they are very well explored. All the Hamiltonians of NMR, EPR, they are very well explored. So if we place spins in magnetic field, we know exactly what would be the interaction of spin with the magnetic field. And these interactions, they can be constructed using Pauli matrices. For instance, if we have this magnetic field spin interaction, it's called Zeeman interaction. For 2 spin system, we'll have 2 states, and the energy of each state would be different. So one would be like omega naught by 2, other would be minus omega naught by 2. So omega naught is basically the frequency at which the spin will start precessing along the field. So one is clockwise precession and other is anti-clockwise precession. So this is the interaction of spin with the magnetic field. Now, the important thing is, in order to apply gate, we need to be able to manipulate the states of spin. And that we can do with the application of radio frequency pulse. So these two states, they have a different precessional frequency. If we can match the energy difference between these two states, then we can do some transition from one state to the other state. And that we can do using radio waves. So radio wave is like another spin and magnetic field interaction, but in this time, the magnetic field is oscillating. So the interaction Hamiltonian is very similar. We have these polymatrices, and this is applied perpendicular to the external magnetic field. So we have spin angular momentum along X and Y direction, and this is at a certain frequency, at certain oscillating frequency, which matches the energy difference between the two spin state. And if we match the energy difference with the oscillation of the magnetic field that we apply, then we can do a transition. And in the rotating frame, we can see the interaction Hamiltonian is very similar to what we had for the Zeeman interaction. Only thing is, in the Zeeman basis, this is off diagonal Hamiltonian. And that's important because if we want to do a transition between these two states, the Zeeman basis, then this interaction has to be non-commuting. So it's off diagonal in that basis. And we can control the length of the interaction, length of the oscillating field that we apply, and that gives rise to different kind of population of the density matrix. The third important interaction for spins is spin-spin coupling, and that is very important if we want to apply gates that involves two qubits simultaneously. And the interaction Hamiltonian is again very well defined. So this is one kind of coupling. It's called J coupling. And here we have two spin angular momentum operator. And if we can construct this Hamiltonian in the product basis, and what we see here is that for this kind of Hamiltonian, which is secular, which is commuting with the Zeeman interaction, we have 4 diagonal interaction terms. And if we divide these 4 terms into 2 subspaces, in the upper subspace and the lower subspace, if we compare the energies, they're exactly opposite. So here it is omega j minus omega j, and in this manifold, it is opposite of that. And this is very important in order to create gates like C0 gate. So for C0 gate, it's NOT gate, which is controlled by one of the qubits. So NOT gate applied to one qubit, but controlled by the other qubit. So in this C0 gate, we are flipping only one of the qubits when the other qubit is in +1 state, or is in +½ state, or -½ state here. So you can see only in one manifold we are inverting, but in the other manifold, this inversion does not happen. And the reason can be very easily understood why NMR helps to create this kind of gate is this term, the coupling term, it's opposite in 2 manifold. So when we create, when we flip one of the, or create a superposition state of S qubit, then the evolution from that state, it depends on the coupling. It depends on how the control qubit is aligned. If it is aligned along 0, then evolution happens in one direction. If it is aligned in 1, then the evolution is in the other direction. So using this simple Hamiltonian, we are able to create C0 gate for NMR very routinely. And NMR has been shown to like we can have specific molecules. For instance, in this molecule, we have 3 NMR active nuclei: proton, carbon 13, and fluorine 19. So we can apply pulses, radio frequency pulses on each of these spins. And each pulse is basically a unitary operator. It's a unitary transformation. We are rotating the spin state or the qubits. So we can have 90-degree pulse, 180-degree pulse. We can also apply C0 gate. We can also have a delay. And during that delay, it's basically the coupling that evolves. So everything that we do in NMR experiments, it's basically a many combination of unitary operators. And they have been used in the past to show to all the quantum gates that have been theoretically proposed to also show Shor's algorithm to factorize, I think number 15 or some number using a 2 or 3 spin qubit system. So NMR is very powerful to demonstrate the concepts of quantum computing, but it's not utilized for any kind of computing. Sorry. Yes.
So it's very clear each has single qubit gates are given by some codes. But could you say again how the 2 qubit gate like a C0? How do we get this detection Hamiltonian realized?
So it's basically, there are many different pulse sequences that have been proposed to demonstrate C0. And basically the main concept is that we want evolution of these two spaces to happen in different direction. Like, I'm not sure if you can see my pointer. So evolution in this subspace and evolution in the other subspace, it has to be in different direction. So from this point of view, if we have, say, positive coupling on that manifold, the evolution will happen clockwise. And then you apply another 90-degree pulse such that this spin, this qubit will go to 0. If the evolution happens in this direction and you apply a 90 pulse, this qubit will go to one direction.
Right. I said this theoretical idea. I'm wondering in the physical system, what is it? So these spins are sitting on different points in the molecule, right? There are different atoms in the molecule or different electrons. So don't they will have to interact now somehow?
So good thing about is that these qubits, so there are two kinds of qubits that we can choose, homonuclear qubits or heteronuclear qubits. Meaning when we apply radio frequency pulses, so the splitting.
The radio frequency pulses are changing.
Yes. These split.
But how?
So this for single spin, but now we want that they change one spin independently of another.
So these radio frequency splitting, it's dependent on the nuclei. The splitting for nitrogen for fluorine 19 is different from splitting from carbon 13. And when we apply a radio frequency, it has a frequency, and that frequency has to match with one of these two nuclei. So the resonance for carbon is very different from resonance from nitrogen. So if we want to manipulate carbon qubit, then the pulses has to match the precession of the carbon. If you want to match precession, if you want to manipulate nitrogen 15, then the pulse has to match the frequency of nitrogen 15. If there are two nitrogen 15, it's possible to even distinguish both of them if they have chemical shift interaction, or if we can do some kind of manipulation to selectively manipulate both the spins together. So this is something which is very routine for NMR experiments. This technology is developed.
Different subspaces invariant under that transformation.
What's
like
your?
You are changing one factor and leaving the others.
Yes.
Yeah, I can see that, but the some point seems to be one that now independence of some qubit. They want to send a pulse that changes given qubit. Not just absolutely, but independence of some other qubit. I'm wondering how that works.
Because it's something similar, like we create resonance. So there is a carbon which is say mutating with 100. The units are like very large numbers, so it's say 100 megahertz. So the carbon spin will mutate with 100 megahertz, and we have say we have say 19F, and that will mutate with almost 400 megahertz. So the splitting, and this is the splitting of nitrogen. This energy is 100 megahertz, and this energy is 400 megahertz. Now, when we send radio frequency pulse, we choose we know what's the frequency of that radio frequency. So this is say 100. And if we, so this wave will only do an excitation from here to here or here to here. It will not do any excitation here because this energy is 400 and what we are sending the wave is only 100 megahertz. If we want to manipulate this spin, then we have to send a wave which has much faster resonance than the black one.
Yes, so that's why this gives signal qubit gains. You send the wave,
Mhm.
it changes one or the other two. But now I'm asking, what if I want to change one independent of the other? What do I do then? I want to send a pulse that changes the one on the right, say, only if the one on the left is in some fixed state. Not in the that's it. Make a CNOT, right?
Yeah, so we don't create CNOT like that. Ideally, we could do that. So I got your question now. So if we see the NMR spectrum, suppose these two are coupled. There is a carbon and there is a fluorine, this is coupled. And if we go and look at the carbon spectrum, if we record carbon NMR, if they are coupled, you would see two peaks. And this two peaks would mean, so this is a transition from here to here when the fluorine was say 0. And this is the transition in the carbon itself when the fluorine was in one state. So the energy is slightly split, and that's because if fluorine is like this, the magnetic field that this carbon, the net magnetic field this carbon would experience would be slightly different compared to when fluorine is like that. So, and that we can see in the NMR spectrum. So if we want to apply a CNOT gate very simply, we can do a very selective transition. We can just only hit this transition with a very soft pulse. It's possible to do that. But then it depends, like there would be a lot of error because if we are doing like that, we might also be doing some non-selective transition here. If these two are very far apart, it's possible to do that. But in NMR, this splitting energy is very small. So here these units are megahertz, and this is only like a few hertz, maybe 10 hertz. So they are very close in frequency space. Ideally, theoretically, we can do a CNOT by just doing a selective transition here. It's possible. But to be sure that the CNOT works for non-selective pulses also, there is a sequence. I don't know the exact sequence, but like there are pulses. Say it's 90, 180. And then there is a evolution time. J coupling evolution happens between the two spins. And this J coupling evolution, it will fan out the phase of the other qubit, which we want to apply the NOT gate, depending on the control qubit. If the control is like this, the phase will fan out in one direction. If the control is 0, then the phase would evolve in the other direction. And then we apply another 90 pulse, and that 90 pulse will either put the qubit in 0 or in one direction, because they are now 180 degrees shifted. And if we rotate, both of them will always be in the other direction. If I remembered the exact CNOT sequence, I would have explained each step by step, but this is the logic. This J coupling evolution is changing the phase. Is it okay or?
Yeah.
Okay. So despite all the advantages of NMR, where we are able to manipulate every interaction very precisely, still NMR is not used for quantum computation. And the reason is quite something which is quite intrinsic to NMR, which is in NMR, we measure a very small energy. What we are measuring is basically like a few hundreds of megahertz compared to other quantum systems where the energies are in terahertz or gigahertz, a lot larger than that. In NMR, this energy is small, and as a result of this small energy difference, the population. So when we take molecules for computation, the molecules do not have a preference to be in one of these energy levels. They can choose, they almost to a very good approximation, the population is almost equal. There is only a slight preference to be in the lower state, which means we cannot really initialize our quantum circuit. There is a very small preference. Like if we take 1 million molecule, maybe one of them would prefer to be in the 0 state compared to 1 state. So this is the major challenge in NMR. The other challenge is the interaction strength is very small. So this interaction is say hertz or hundreds of hertz, meaning you will have, in order to apply a C0 gate, we may have to wait for 20 or 30 milliseconds. So if we have a quantum circuit, each circuit will take a long time for the evolution to happen, because the strength of Hamiltonian is very weak in NMR. So it's good to test concept, but it's not good for real computation. So polarization is a problem. And polarization is a problem because we are measuring a very small energy difference. And if we can somehow increase the energy difference, then the molecules will have preference to sit in one of these, more preference to sit in one of these energy levels. And this is exactly what happens with electrons. So electrons, they also have spin, and their spin angular momentum is a lot larger than nuclear spin. So the energy difference is large, and they have they can be better initialized. If we want to make things better, we can go to molecules and exploit the electronic state properties of molecule. In that case, the polarization is almost unity. So if we take 1 million molecules, all those 1 million molecules would be sitting in this configuration. So these systems can be better initialized. But
So what is the third system?
it's exploiting. So here we are exploiting the spin property of molecule or matter. Here we are exploiting the electronic states of the matter. So normally most of the molecules that we see, they are in ground state. But if we shine light, the molecules will go to an excited state. And in the ground states, most of the molecules, like for these energy levels, most of the molecules, they would be sitting in this ground state. So they are almost 100% polarized compared to here, where polarization is 10 to the power minus 5.
What is the electron?
This one?
Yes, so this is one electron? Or?
This is one. This is like energy level of 1 electron. But if we take many electrons, this is how their population would be distributed.
Then, okay, this is maybe a demonstration of why gap systems are much better to use gap system on.
I'm not into semiconductor, but
exactly the same thing.
okay.
The difference between the ground state and the next excitation.
Yes.
There is a constant in there. So as the system is uniform constant, uniform lower bound on the difference between the ground state and the next excitation. Such systems are better to use in storing information because of maybe this. Just comparing.
Yeah, I can.
It's the same thing, having the gap and versus not having the gap.
Yes. So I think you're right. If we have larger gap, then system is confined more. The probability of confining it to one state, the lower state, is higher. So and this is called Boltzmann distribution of molecules. So the best would have been if we could have used the electronic state. But the problem with electronic state is the uncertainty in energy. There is an uncertainty principle. So here the uncertainty is quite high, and the coherence time would be a lot lower here compared to in the nuclear spin case. So one of the idea that people are working in the spin community is to exploit this electronic state, but transduce the polarization from the electronic state to the electron spin state, and then do all the computation on electron spin state. So it's like we want to measure things here, but before we measure, we want to do some pre-preparation, and that pre-preparation would basically increase the polarization of the system. I will show you one example of that. One of the best candidates for physicists has been NV center, or nitrogen vacancy center. So it's basically in carbon, in diamonds, there are sometimes defects where two carbon atoms are missing, and one of those missing carbon atoms is replaced by nitrogen atom, and the other one remains a vacancy center. So this is called NV center. It has very favorable optical property, which is we can shine light on this one, and by shining light, the molecule goes to an excited state, and then it can do inter-system crossing. So from a triplet, it can go to a singlet, and then it relaxes back to the ground state. But by doing so, the population in the zero state, it goes far beyond the Boltzmann, far beyond the thermal equilibrium. So by doing optical pumping in this kind of molecule, we are able to generate a very well initialized state. And this is something which has been very well explored by physicists. And we can apply gates, which are basically microwave pulses here, and read out those manipulation optically, which is a lot more sensitive than reading out through inductive coupling, reading out through coil. So all these things have been shown. So NV center would have been a very ideal qubit candidate. But there is one problem, and that problem is we cannot scale up NV center. We cannot have 2 or 3 or 4 NV centers all together in a controlled way, because these are some defects in a crystal. And to create these defects in a controlled way, where we are able to exactly know the distance between 2 NV centers or multiple NV centers, this is something that could not be done despite several attempts. So that's the problem with NV center. So what I tried to do in my postdoc was to create molecular analog of crystals. So if we can synthesize design molecules which will have similar energy level like that of diamond, we can optically pump these molecules and then have a very hyperpolarized molecular system. So we can initialize them very well if we can mimic their energy levels to that of diamonds. So that's the goal that I had, and something that I want to explore in the future. So when we optically excite a molecules, the electrons which are there in the molecule, they get some energy, and they have some energy which will separate them. Like the average distance, if we have to think classically, that slightly increases, and then the molecule can have different path. It can dissociate, or it can do intersystem crossing, or it can relax back to the ground state. So it becomes very complicated in the molecular system, like how to design the energy levels that would match with that of diamond. And there are many parameters also. When we do these things experimentally, we need to have a magnetic field. So the strength of magnetic field would be important. And the system that we wanted to design was having a chromophore. Chromophore is something that can absorb light, and that chromophore is coupled to a radical center. So this is the initial system we had. So now what should be the coupling between the chromophore and radical is a parameter. What's the molecular orbital symmetry is another parameter. So there are many parameters in this schematic. So that is something which makes the problem very complicated.
So what is happening here? You are taking the piece of product between three-dimensional space and two-dimensional space, like spin 1 and spin 1 half.
So we have spin 1, yeah. So I'll come to that later. So if we have two systems, and so basically now we are into a system which has 6 energy levels. And depending on, so if we look at the interaction Hamiltonian, so we have these diagonal terms and we have many off diagonal terms. This system can behave like a spin 1 and a spin half, two spins which are weakly coupled, or it can behave like a different system. It can behave like a spin 3/2 and a spin half system. So it's how we sum the angular momentums from J S1 plus S2, from mod of S1 plus S2 to mod of S1 minus S2. And the coupling strength, basically these off diagonal elements, they determine what would be the new basis set in which we should work, or we should think these interaction terms. So in our case, we wanted it to be a very strongly coupled spin 1 and spin half system, such that it forms a quartet system and a doublet system. So I am skipping some slide here because of time, but let me actually see if I have those system. It's not here. So it's basically a 6 energy level system. And within that 6 energy level system, we have a quartet manifold and we'll have a doublet manifold. And we need to again apply some pulses, basically some kinds of gates, to know in what system the molecule, like once we shine laser light, in what configuration does the molecule go to, whether it goes to a spin 3/2 system or a spin half system, and what would be the polarization of each of the individual systems. So we do these kind of experiments, and one experiment that we can do to know in what level they are is nutation experiment. So whenever we do any NMR experiment, or even if someone is doing NMR quantum computing, there is one experiment that has to be always done, which is nutation. So we have this, say, a density matrix. What we do is we have RF or microwave pulse, and they are off diagonal. Using those pulses, we nutate the population between the, say, any of the two diagonal elements, and look at what's the nutation frequency, at what rate we are able to nutate the population from one state to another. And this nutation frequency would give us the information about the spin quantum number, whether we created a quartet system or whether we created a doublet system. This information can be obtained. So, so this is something we do for characterization of the photoexcited system. And I will skip a few slides here. So with this, finally, using all these studies, we were able to develop molecular system which, upon photoexcitation, went into quartet state. So these are the features of quartet state, and it got polarized way beyond the Boltzmann. So if Boltzmann is, say, close to 0, we polarized it to a very high level, and the polarization lived on that molecule for quite some time. Here it is around 7 or 6 or 7 microsecond. So the polarization lives for a very long time. These polarizations, they have feature depending on at what magnetic field do we measure. The polarization intensities are different, but let's not go into that detail for now. And also, depending on at what temperature we are creating polarization, we may need to design different kinds of molecule. If we want to design a molecule for high field or a molecule for higher temperature, we may have to increase the coupling between the chromophore and the radical. So these are all some complexities that people are trying to solve. I want to quickly move on to the other part of my talk, which is spin coherence. With in NMR, we had the problem of low polarization, and using optical pumping and using electron spin, we were able to create high polarization in those spin system. But when we did that, compared to nuclear spins, the relaxation of electron spin is a lot fast, because electron spins, they have higher gyromagnetic ratio, meaning the magnetic field that they have around them is extended to a larger distance. And if that happens, they have more tendency to interact with the environment. So the decoherence in such system, although we could polarize them better, but then they have faster decoherence. So having a system which is highly polarized and also whose relaxation would be slow is important in order to not create the another problem of short decoherence time. And you all understand why decoherence is important. With pulses, we are creating some coherence term, and these coherences, they have the information about whatever operation we are doing, but they also relax back to the equilibrium, and there is a relaxation rate. So we want these relaxation to be very slow. So we need to identify what are the different mechanisms through which spins relax to their ground state. One of the very important mechanisms for these kind of system is flip-flop of two nucleus. So around electrons, we have many nuclear spins. And if the nuclear spins, they flip-flop, they are basically changing the magnetic field which is at the electron center. Because each of these, they are magnet, and if they go from this state of the magnet to that state of the magnet, the net magnetic field around the electron, that would change. So one of the things that we have to do in order to have longer decoherence time is to minimize this flip-flop. In the molecules, the first class of molecule that we synthesized, we had a lot of methyl groups. So it's basically like a CH3 groups, and it's rotating. When those molecules, side chain of the molecules, when they rotate, they also generate an oscillating magnetic field around the electron center. And anything that is oscillating, it can lead to a transition from one state of the qubit to the another state. And that's a source of decoherence. So we need to, in order to have longer coherence time or decoherence time, we need to minimize all those kind of motion. One thing that we did, one strategy we adopted is to fuse this CH3 group into a cyclic group. So it's a very minute change, minor change here. So these methyl groups, they are fused. And if we do that, we can compare the decoherence time for different states of the molecule. So these are, I didn't go into details, the satellite, central, and the ground state, but we can see the purple one, which is the new design where the CH3 groups were fused. They have much longer decoherence time compared to the red one.
Having those two, you are also creating an extra interference with the rest of the system. Then how can you tell that you are decreasing the decoherence?
So those nuclei, they could have ideally been used as a qubit system. But here in our case, this particular case, they were leading to faster relaxation of the coherence of electron spins. So if we want to have multiple qubit system, we will rather want to have these fused system, many of these fused systems coupled to each other, and not this kind of system where a nuclei, unwanted nuclei, can interfere with the coherence of the electron spin. So if it can be controlled, it's good. But if it is not controlled, then it will lead to error, because we don't know in which state exactly the molecule is sitting in. Does it answer your question, or?
Yes. Yes, so you are talking only about the decoherence of the electron.
Of just the electron spin. There is one more, sorry. Yeah, no, you can ask.
Going to change the state of the system.
They are?
Not going to interfere with the state of the system.
The nuclear spin, you mean? Nuclear spin will not interfere with the state of the system. Yes, that's correct. Because the energy level that we are talking about, these are all electronic energy levels. And these energy levels will not change depending on the state of the nucleus. Because nuclear energy is very, very small compared to these energy levels. These are like in terahertz. And the nuclear energies are only a few hertz. They are good enough, they are strong enough to cause a transition within the electron spin manifold, but they cannot change the overall energy landscape of the molecule. They can cause a transition because they can fluctuate, and that fluctuation will create an oscillating field, and there can be a transition within the molecule. But the overall energy of the system would not change. The energy landscape would not change. So even if we fuse them, more or less, the energy levels are the same, and that we confirmed by looking at this polarization pattern. For this CH3 and for fused groups, the polarization patterns are the same. One last thing is, so we saw like electrons, they are very good when it comes to initialization, and nuclear spins, they are very good when it comes to coherence time. So it might be possible, like say if you are doing a computation where we want to store some information which is there on electron for longer time, we can do a trick which is again common for NMR people, and that trick is to relay the information from one spin system to another spin system. So we can do some manipulation on electron spin and store that information by transferring that information to the nuclear spin. So here, for example, on hydrogen atom, proton atom, and that will require some again some creating some kind of resonance, but those experiments have been developed, and one of my research is to transfer polarization from electron spins to the nuclear spin, and they are again done with using some radio frequency or using some microwave pulses. And here I would just like to show how, like experimental demonstration of what we could achieve. So we created some initialized some polarization on electron spin, and on x-axis here it's basically some condition that is related to the microwave. On the y-axis it's the polarization of the electron spin. So we create a certain condition where the polarization on the electron spin that's lost, and then when we move away from that resonance, we see conditions that polarization was still maintained. So at this resonance condition, the polarization is transferred to the nuclear spin. Then we can have a very long delay, and we see that during the delay, the polarization, we can create experiments where we can give a very long delay, and the polarization during this long delay, what we see is the polarization is still there on the nucleus. And this time scale is a lot longer compared to the time scale for which we can hold the quantum information on the electron spins. Because nuclear spins, they relax very slow, so there is no decoherence on the nuclear spin. And what we can do is the third step, we can transfer back the information from the nuclear spin to the electron spin. And in this plot, you see at certain resonance condition, again, the intensity on electron spin is gained back. So we do some manipulation on electron spin, transfer that information to nuclear spin, and that can hold the information for milliseconds and then transfer it back on electron and measure it. So these things are possible in magnetic resonance. One other thing which I am interested in, so right now when we do sensing, for example, MRI, it all uses bulk property of the molecule, which is very much classical. So if we do MRI, it will take at least a couple of hours to have a good MRI. And the reason is, again, the initialization. MRI is basically some kind of NMR but imaging, not spectroscopy, but imaging. But the problem is still there. The two levels, they are almost equally populated. So in order to see something in MRI, we have to scan for a very, very long time. The sensitivity is very bad. With optical pumping, with the transfer from electron to nucleus, we can increase the sensitivity of MRI. So an MRI scan, which normally typically takes hours, can be done in a few minutes, maybe in seconds, if the technique can be very implemented. So for me, working on these kind of problems, molecular spin qubit is very important, not just from computation point of view, but also for other quantum technologies. And most important is for me is sensing. So with that, I would like to conclude. I hope I have shown that spin states can be polarized using combination of light and microwave. Then if we want to, we can design molecular systems that have longer decoherence time, and we can do relay of polarization from electron to nuclear that may have utility in storage of information. So with that, I would like to thank you all for your attention.
Maybe no technical question. So when you mentioned that the molecule is stable and because without the stable But as far as I understand, in NMR, you need some like heavy isotopes, right? Of atoms, right? Like, for example, you need material, I think is more
Mhm.
important. So how do you like construct that molecule? Like, how do
Mhm.
you-
So, no, so in NMR, we have hydrogen 1H, and then it has isotope deuterium, and both of them are NMR active.
Oh, right, sorry.
So the
Carbon 13. is-
Yes, so carbon 13 is also NMR active. Difference is why sometimes they substitute hydrogen with deuterium. The reason is, if we look at hydrogen, it has a strong gyromagnetic ratio. So it interacts a lot more with the other nuclei compared to deuterium, which has the same electronic property, but the nuclear spin of deuterium has 10 times lower gyromagnetic ratio. So its magnetic field is confined to a very small radii, like less than 1 angstrom, compared to proton, which can interact with another nuclei, even if it is 10 angstrom apart. So if you want to minimize sometimes interference from other nuclei, and if certain proton is not needed, we can substitute that with deuterium. That will ease out the experiment. So even for development of qubits, suppose we want only one hydrogen atom. Normally hydrogen atoms, they are ubiquitous. There are a lot more hydrogen atoms than any other atom. You want only one hydrogen qubit. You can deuterate everything else. And those deuterated will have very minimal effect. They will have an effect only within a radius of less than 1 angstrom. And average bond length is around 2 angstrom. So the effects of those nuclei would be almost nullified in our experiment. So it's for that reason that people deuterate most of the time. Does that answer
Yes,
your
I mean,
question?
I was also like curious about like how easy it is to make such a, like, because you said scalability, where you need like many of those.
Mhm.
I mean, right now we're at early stages, but like, say if you want to make what's a computer, a lot of
Mhm.
those, is it easy to
The
make?
scalability is a lot easier in molecules than in crystal.
Right.
So like I'm not an organic chemist, but I know organic chemists, they can also synthesize peptides or protein molecules. So they know how to have an architecture, a scaffold, which is very long. So those things can be done. But the thing is, what should be the design of that molecule? This is something which most of the chemists, organic synthetic chemists, they do not know what design would help for quantum technology. That's the problem right now. Yes.
So if I understood correctly, each qubit, you need a different molecule for each qubit.
No, we don't need a different molecule. We can have one molecule. For example, if I go back to that example of NMR. So you see, I'm not sure if it is highlighted enough. So this is basically a one molecule. It's a simple molecule. So instead of methane, there we substitute 2 hydrogen with bromine and then 1 with fluorine. Okay. So
Atom for each.
yes, so different. It's not the atomic property that we are using. It's rather the nuclear spin of the atoms. So here we are using the nuclear spin of carbon. So this is a spin half nuclei, and this is again another spin half nuclei, but all 3 of them, they have different precision. So in order to do any manipulation on hydrogen or carbon or nitrogen fluorine 19, we need a different radio frequency pulse, and that helps to do manipulation. We could have a qubit where all of them are say more or less similar, same homonuclei, and they will have slightly different energy because of an interaction which is called chemical shift. But manipulating them would be very tedious.
So how do you put a lot of qubits? Like 2 of these things together,
Mhm.
how do you excite only one of them?
If we have 2 of the qubits and you want to excite only one of them, I think so. When we are doing excitation right now, I don't think any NMR technology is developed where we can, out of 2 molecules, we can only excite one. But if we can do NMR more on chip, like just like right now, when we have NMR, we have like a big coil, and within that coil, all our molecules are. But if we can fabricate NMR. And for have molecules, and for each molecule, we have a circuit. Then we can control all of them. And that's how like computation is done right now. We are controlling each classical bit using a different circuit.
So,
Maybe like, sorry.
yeah, so this carbon it has to be done 3-half system, or it's again 1/2 system?
This carbon,
Yes.
carbon is spin half.
System. So is it very kind of well known, let's say, classified, categorized that every chemical thing is it either spin half or spin 1 or spin 3?
Yes, this is like for all the atoms, for all the fundamental particles, we know their spin quantum number. That's very well
And
specified.
the spin 1/2 is most convenient.
Spin 1/2 is more convenient because there are only 2 energy levels.
Yeah, but here I'm kind of puzzled a little bit with the carbon, because if it's just spin 1/2 and it's connected to 4 things,
Mhm.
then 2 connections are going to be real, but the 2 others are going to be trivial. Because spin 1/2, it's the Hilbert space dimension 2. So, and this, in order to have interaction with 4 other things, it needs to be more than spin 1/2.
So this is yes, like if we look at the product basis, then this is like a 8x8 Hilbert matrix. But within that, there you will have manifolds, and not necessarily the energies would be different in different manifold. It depends. Like for example, here we have 2 spins, and from 2 by 2 it became a 4 by 4 matrix, depending on what is this interaction, J coupling. Here I'm only showing the J coupling. So we have the Zeeman interaction on the diagonal, and on to this energy we are adding J coupling. So it depends what's this interaction strength. If it is large, then yes, it is no longer an ideal spin half system. It is more like a spin half cross, like a spin 3/2 system. We can say that, or a spin 5/2 system, or a spin 2 system. But it depends on coupling. For NMR, these interaction strengths are still very large that we can consider them to be a spin half system. So if the coupling was large, for example, in the electronic spin system, we had this spin 3/2 and spin half. The coupling, these J couplings are large enough that it's no longer a spin 1 and spin half. It's rather a spin 3/2 and a spin half system. So it depends on the coupling strength. The new eigenbasis would basically we have to diagonalize that. And on diagonalization, we have to see how much of contribution is coming from these off diagonal terms relative to the difference between the corresponding diagonal terms. Did I answer your question, or?
Yeah, I still need to think about this coupling of 4 atoms around the carbon, and how.
So-
the dynamics in just the spin, just the electron around the space, the valence electrons make the bind there.
You can couple them, but I mean for the interaction. The interaction then.
So if there was just one carbon atom, if you would have seen NMR, it would have been like this. If you have 2 spins, then we get a doublet. So one transition in each of the manifold. And if we have one more, each of them would further split. So you will have a doublet of a doublet. Okay, but these ones, the scale here is like this interaction strength is say 100 megahertz. Here it is 100.00001, and this is like 99.9999. So this difference is very small. So as long as these differences are small, it is still a spin half system. Only if the coupling becomes so large, then it's this 2 spin half. If we have a spin half and another spin half, the net spin angular momentum is basically like a mod of spin half plus spin half to this. And here it will be basically a triplet, a spin 1 or a spin 0. And here also you have basically this triplet will have three projection -1, 0, 1, and this has just one projection. In the end, you have four energy levels here, four energy levels here. So if we follow all these formalism, there is no problem. Like the maths or the spin property is still the way we understand it. That understanding is valid. I'm not sure how to put it in a better word, but it matters only if coupling is large. Then we are in this basis here. If coupling is weak, then we are still like a two separate spin half system.
So I'm asking because usually if you are talking about the chain quantum spin system, the system of the chain, then you can consider spin one half circular now chain, just interaction and left and right. Spin one half, and you can put spin one or spin three too. That's totally fine. But if you have like hexagonal honeycomb lattice, then you cannot put one half, spin one half. It's not enough for the full interaction. This is what I know. And then you need with the hexagonal lattice, you need spin one residing at every vertex in order for the interaction with the two others. Maybe this is okay. I'm working the theoretical thing. Maybe I'm missing something in the practice. Of course, I believe that one has spin one half, but then there is something we are missing in the interaction, and this has to say something about the interaction. But it's not full interaction with the others. Is the top and the bottom the same? Because the left and right.
The top and no, the top and bottom, they are different. The top is hydrogen, and the bottom is fluorine 19.
Okay, we're going to continue the discussion later. Let's thank Asif for the